In this lecture, I will introduce how to interface a microcontroller with an accelerometer. First, we must understand how accelerometers work. Accelerometers rely on piezoelectric crystals, which produce a voltage in response to their compression. These materials have very special properties, and under certain compression they produce different voltages than under other compressions. They are coupled with a spring mass damper system that allows the mass to move up and down in response to the orientation and the movement of the accelerometer itself. As that mass moves in orientation relative to the piezo crystal can become compressed, and under different compression will output different voltages. This allows us to determine how an accelerometer is oriented and how it is moving through the environment. Typically, accelerometers produce analog signals. So some may be digital, and that is often the result of a digital signal being created from a natively analog signal through an analog to digital conversion. Typically, accelerometers have three axes of acceleration. So we have an X, Y, and Z orthogonal axes that we can measure from. And the acceleration is typically expressed in g's, which are multiples of the acceleration due to the Earth's gravitational pull. In SI units, 1g is equivalent to approximately 9.8 meters per second squared. And so we can use that to determine the orientation of the Earth's gravitational pull relative to the orientation of the accelerometer. And our analog output will produce different voltages in response to the number of g forces experienced on each of the three axes that we are measuring analog signals from. So we can use this to detect the pose of an accelerometer. This is the technology that is used in smartphones and tablets in order to determine whether images or various applications on the screen should be displayed in portrait or landscape mode. The accelerometer can be used to detect how that orientation of the Earth's gravitational pull is relative to the screen. And we can use this to detect how various other bodies are oriented, and can use this in a similar way to a gyroscope to determine whether something is tipped over or is level. When it is turned, the influence of gravity changes and applies to different axes relative to when it is in another orientation. So here is an example. We have a single accelerometer, and we can showcase it in 6 different orthogonal positions. So if you see the position up here in the top with the dot in the top left, if our x-axis in this orientation is going up and down, our y-axis is left and right on the screen, and then the z-axis is in and out of the screen, then what we're seeing here is in this position, our x-axis is experiencing 1g. Gravity is pulling down with the acceleration of 1g in this direction. If you were to rotate this 180, the x-axis would still be experiencing 1g of acceleration, but it would be going in the opposite direction relative to the piezo crystal associated with the x-axis. And so in this case we would see positive 1g here, negative 1g there. If we were to rotate from this top position 90 degrees to the right, now the y-axis is the axis experiencing the acceleration due to the gravitational pull of the Earth. And so we can see 1g going downward here, as opposed to over here, if we rotate 90 degrees and 90 degrees again, a full 180 here, now the y-axis is experiencing that 1g in an opposite direction. If we lay the accelerometer flat, now the acceleration due to gravity is going perpendicular to the top and bottom of the chip, and so here we are seeing the z-axis experience 1g or negative 1g. What we need to consider when we're interfacing an accelerometer are the voltage requirements. So we need to understand what voltages will be output from the accelerometer and what voltages are necessary to drive the accelerometer. And so our accelerometers that we are going to use in this class rely on a controlled voltage range. they can take in a variety of voltages, but putting too much could actually damage the accelerometer. And so the accelerometer boards that we will use have an onboard voltage regulator to ensure that we are not giving too much voltage. And in fact, that voltage regulator will allow us to drive an accelerometer that relies on far less than 5 volts with a 5 volt input signal, so we don't need to produce a different voltage than what we can get from our standard USB signal. We also need to consider, when choosing an accelerometer, the number of G's that we are likely to experience. So the application will drive the choice of an accelerometer. If you have something that is going to experience rapid acceleration, let's say you're trying to measure the acceleration of a rocket, a missile, some sort of space shuttle or something like that, you're going to need an accelerometer that can handle very large G's. If you are just trying to put an accelerometer into a tablet and may just reorient it, perhaps you're trying to measure steps in a step counter, you don't need very high G ratings in order to do that. And so the application will determine how many G's we might need when choosing an accelerometer. We will use 2 different accelerometers in this course. Some of you have been provided with a board that uses the ADXL335. This is a 3-axis accelerometer, and it can measure accelerations between plus and minus 3 G's. It requires an input voltage of between 1.8 and 3.6 volts. However, that is provided because there is a 3.3 volt regulator on the board. So what we will provide to it is the VDD signal, which is 5 volts, and that voltage regulator will step that down to the needed 3.3 volts for the accelerometer. The ADXL335 outputs a 0G signal at nominally half of the input voltage. So we will see approximately 1.65 volts coming out when we are experiencing a 0G situation on any given axis. And there is a tolerance on that, just like almost any device that you would buy that is man-made. There are imperfections. It is not going to be to an exact standard. So there is a plus or minus 10% tolerance on that. So when you're at 0G, you may see 10% above or 10% below the nominal 1.65 volts. There is a sensitivity, which is expressed as a voltage on top of or below the 0G voltage in response to the acceleration due to gravity. So if a particular axis is experiencing 1G, then it will add or subtract nominally 300 millivolts, but that also has a 10% tolerance on it. So with the 10% tolerance accounted for, it will add or subtract between 270 and 330 millivolts for every G that it experiences. So if we are looking at something at 1G, then nominally we would expect 1.95 volts. That is the 1.65 for the 0G condition plus the 300 millivolts for the 1G of experienced acceleration. But given the sensitivities, we can, or the tolerance on our sensitivity and the tolerance on our 0G voltage, we can see a 10% swing upward and downward on both of those values. So at its maximum, with a 10% swing upward on the 1.65 volts and going all the way to the extreme of adding 330 millivolts, we could see as much as 2.15 volts. On the opposite extreme, if we were all the way down to 10% below the 1.65 and then we were to be only at the 270 millivolts right there, we could experience as low as 1.76 volts. Likewise, at negative 1G, we can experience nominally 1.35 volts, but that could range anywhere between 1.16 and 1.55 volts. And you see the other voltages on the screen. For 2G, you'd see approximately 2.25 volts with tolerances associated with that. At negative 2G, you'd see approximately 1.05 volts. And at 3G, you would see as high as 2.55 volts. The other accelerometer, the ADXL326, is very similar in pinout, very similar in orientation to the ADXL335. It is a 3-axis accelerometer. We will get data from the X, Y, and Z axis. It has the same voltage regulator on board, and it will allow us to put in our VDD and ground reference. But the difference is that this can handle a range of plus or minus 16G. And in order to accommodate that large of a range within the same voltage restrictions, it has a much smaller sensitivity per G. So nominally, it only has a sensitivity of 57 millivolts per G, and given a 10% tolerance on that, that means for every G that is experienced, we can see a change in voltage of between 51 and 63 millivolts. So what that will mean is when you reorient the position of the ADXL326, you're going to see a much smaller change in voltage going from one position to another than you would with the 335. When we are trying to process signals from the accelerometer, we must use an analog to digital converter. So we cannot natively process analog signals. We must take in those analog values and convert them into digital signals that we can process. We are going to use a separate channel for each of the three axes. So we're going to use 3 of our analog inputs on our PIC processor to process the x-axis analog, the y-axis, and the z-axis. You can recall from a previous lecture that there are 28 analog inputs on the PIC16F1719 microcontroller. And you can see them here in groupings based upon their digital port that they are associated with. Some of these will be good choices for us to use. Others are pins that are already dedicated to other features. So for example, our AN0 we know is already hardwired to the potentiometer on the board. So we do not want to also put our accelerometer on there because the two analog signals would interfere with one another. Since we want to display the accelerometer data on the LCD, we also want to avoid RA2, RA5, RC3, and RC5. So we do not want to use AN2, which is associated with RA2. We don't want to use AN4 associated with RA5, and we don't want to use AN15 associated with RC3, and we don't want to use AN17 associated with RC5. Those will all be used for LCD writes. We also know that C0 and C1 are associated with our microbus. They are not available for analog to digital conversion, so we don't have to worry about putting connections there. Where we will actually connect is AN5 through 7 down here on port E. And so we are going to use RE0 through RE2, which is AN5 through AN7. We'll put the x-axis on AN5, the y-axis on AN6, and the z-axis on AN7. And that will be what we will use to digitize our signal. So, in order to write the code, there is an order of operations that we will follow. What we are going to do in the lab that we're going to do this week with accelerometers is we're not going to use interrupts. We are going to turn off interrupts. This will give you practice in polling, and we'll talk about that in just a little bit. We are going to use our Ancel E to set up the analog inputs. So since we're using port E, Ancel E is associated with those corresponding analog pins. We're going to make sure that those 3 pins are all set up to work in the analog mode. Likewise, we're going to use Tris E to make sure all of those pins are set as inputs. Since we need to use the LCD, we need to make sure that we have configured RA2, RA5, RC3, and RC5 as digital outputs. And then we will use the ADCON1 register to program in our write justification. We will program in the sampling rate, and we will program in the boundary voltage being the plus 5 volts from the VDD and the ground signal VSS. Then we will call our LCD initialization function, just like we've done in previous labs, and that will set up our LCD to work for us. That will all be done in a part of main that only needs to run one time. All of those configurations will be done exactly once. Then we will get into an infinite loop, which will continue to sample so long as our code is running. Within that infinite loop, we're going to configure ADCON0 to set up for the current channel that we are sampling. And we will make sure that our AD-on bit is set so that we enable the analog to digital conversion module. We will then set the go bit, and that will say go ahead and perform the analog to digital conversion on the selected channel. We will do polling, which will simply be a while go with a semicolon after it, that will simply wait until the go bit goes back low. So when you set the go bit to execute the analog to digital conversion, the go bit will remain high until that analog to digital conversion is finished. Upon completion of the analog to digital conversion, the go bit will go back low. So this will be an example of polling. During that time, we can't do anything else. We will simply wait for that to be finished. Once we have that, we will store the analog to digital conversion result in an array of unsigned integers, and we will then display it to the screen. We are going to collect data from all three axes before we proceed to display our data. So we will repeat our configuration of ADCON 0, perform the A to D for the other two channels, doing polling on both of them, making sure that we have the data, and then writing it into our array. And then finally, we will clear our LCD, return to home, and then write out the data to the LCD. We will, in this lab, write out our A to D value and write out the voltage, and we will put it on the screen and wait for 1 full second so we have enough time to record the values that we are seeing. Then we will loop back and continue to do the digitization again. The accelerometer board will require a voltage and ground reference, so we're going to use VDD for our plus 5 volt input that will be regulated, and the ground signal. You have pinouts on your board to provide that, and we will use the connector wires that you picked up from the lab. The three outputs, AN5, 6, and 7, you can connect to the appropriate pins. The pin header has pinouts for RE0, RE1, and RE2, and so we will make those connections to connect our X, Y, and Z axis.